Welcome to this Sahara 4 exercise. In this exercise, we will calculate the distribution coefficients that explain the relationship between the injected water and how much of that injected water is affecting the producers nearby. So let's go to our Sahara project, and as we discussed previously, the distribution coefficients are going to explain, let's say in this layer, in the layer number 4, that is the one that we are plotting now in the map window, how much of the water being injected in the injector D25 is going to affect the two producers. For example, let's say that in this layer, this well D25 is injecting 100 cubic meters per day, so we may have a 50-50 relationship. So the total water that is being injected into this flow element is 50 cubic meters per day, and 50 here. We may have a 30 and 60 relationship. The net, the total of the water being injected doesn't necessarily going to sum the 100%. So in that way we can represent the leakage of the system, of how that not all the water that is being injected is being utilized properly for secondary recovery. Some of it might be lost to the system, so that might be considered as well. So the idea is to have a distribution coefficient that is going to be associated to each different flow element, that is going to explain the relationship between the total water injected and how much is actually affecting the producers nearby, and how that water is distributed between the different producers. Let's go to simulator, pattern and coefficients, and here we have the option initialize coefficients. So here we can select in which wells we will do the calculations and in which layers. In this case we will do it for all of them. We want to initialize the coefficients for all the flow elements that are present in the project, and here we have the different methods that we have available. Here we have angular. This is 100% based on geometry. This method is going to do the weighting based on the angles of the flow elements in the injector well. The coefficient of each element of the injector is the ratio of the angle of each element to 360 degrees. So let's say that of the total, let's go back to our example, of the total 360 degrees that we have here, only, let's say, 45 or so is being occupied by this flow element, and other 45 or more or less is being occupied for this flow element. So only that relation, that proportion from 45 to 360 is going to be considered for the coefficient. Remember that when you use the angular method, most of the cases you won't have a 100% total distribution, so a lot of water is going to be lost. That is why, except if you have very irregular pattern, you don't want to actually use this method in most of the cases. Let's go back to the different options. Here we have pore volumes. No, sorry, we have initial confidence. We have the angular pore volume, or weighted by pore volume. Weighted by pore volume is going to use is going to calculate the coefficient of each element of the injector based on the ratio of the pore volume of each element to the total. So let's say that we have, for example, let's go back to our example here. Let's say that this flow element has a total of 5,000 cubic meters of pore volume, and this one has 7,000. So this one is going to proportionally have a little bit more. So the totality of the injection, we will have like 60% in this injector producer pair, in this flow element, and 40% in this other one. So the calculation is going to sum all the total pore volume of all the flow elements that are associated to this injector, and then it's going to distribute proportionally based on the pore volume of each different flow element. Here we have angular and pore volume, which is a combination of both of them, of the angular method and the pore volume. The injection is going to be subtracted as a function of the angle of the patterns, and this value is then going to be distributed or weighted among the different flow elements based on the pore volume. Here we have weighted by production. In this case, the flow element, the coefficients will be calculated based on the production of each of the different producers So in this case, let's say that this producer has double the production of this one, so the resulting coefficient is going to be 66 for this one and 33 for this other one, because we have double the production here than here. So we have 2/3 of the injected water as well being associated with this producer, and 1/3 with this other producer. So in this case also you're always going to have like 100%, same as with the pore, as weighted by pore volume. That in that with that option as well, you will have 100% of your total water injected in that layer is going to be affecting totally the associated producer with the flow elements. So let's go back to the options, and here we have angular and per volume, and map. Well, here with map, you will select one of the maps that you have available loaded in the project using one of the functions here. The idea is that with this method, you will consider a volumetry taking the flow elements as a polygon. Given a pattern centered on the injector, all the different elements are taken and the volumetry is calculated using the selected map. So if you have, for example, let's say that you use the pore volume map here, it will create the same result as weighting by pore volume. But if you use the, let's say, the net thickness map, the is a volumetry of the amount of net thickness inside each of the different flow elements is going to be calculated, and then the one that has the most effective thickness net thickness, sorry, inside the flow element is going to have also the biggest coefficient. So in this way it's similar as weighting by pore volume, but you can weight it with different maps that are not necessarily the pore volume that was calculated using the pore volume map in the previous step. And finally we have distance here. With distance, the idea is to just assign the coefficients considering the distance from each producing well to the injector well on the grid center on it. So those wells that are further apart will have a lower coefficient, less water is going to be assigned to them, and those that are close to the injector will have a higher coefficient. Um, so that's another way to calculate the coefficients that are going to do the connection between the injected water and how much is actually being how much is actually affecting the nearby producers that are connected by the flow elements. So for our sample, we will use the method weighted by pore volume, and here we will select it for all the dates. So we want to calculate do the calculation for all the dates. You can as well, if you desire, instead of doing it for all dates, you can select an initial date to do the calculation, the coefficient calculation. This is useful if for some reason you want to do combine different methods with different dates. You may want to start with angular and then switch to weighted by pore volume, or switch to angular and pore volume. You can do it using this option. In this case, we will just use weighted by pore volume for all the dates. We will select all the layers, we will select all the wells. We will consider an efficiency of 100%. Here you can manually consider leakage as well if you don't want to have like 100% of the water that you are injected being used for the simulator, or being affect the producers. You can modify that as well. You can reduce the efficiency with another number, let's say for example 90. In this case, just 90% of the total water being injected in the layer is actually going to be used for the simulator. So let's just consider 100% here, and let's just calculate. And now we see that we have our coefficients calculated. So now let's see what was calculated here. Let's go to flow elements, and first let's check the calculation. Let's select pore volume and coefficient. So we can see here that we have 50 here in this as pore volume from this injector to this producer, and almost 40 here from this injector to this producer. So now let's see what was calculated as coefficients, and we can see that we have a little bit more. 56% of the water being injected in this layer is being assigned to this producer, and 44 of the total water being injected in this layer, 44% is assigned to this injector, which makes sense based on the pore volume that we have calculated 1,000 of barrels here. So we can see that that's how it was calculated. We can check that based on the method that we use, always the sum of the coefficients is going to be 100%. So we can check that for the different injectors and producer pairs. But that should be the case. Remember that when using angular, or using angular and combined with the weighted by pore volume, in those cases you may not have 100%. That is going to be based on geometry. Also, with the other methods that always are going to ensure that you have 100%, you will have your injector efficiency to reduce that efficiency from 100%. That will be all the total water being injected in the layer is going to be used in the simulator. Is going to be assigned totally to the different producers. You can reduce that manually by reducing the injector efficiency. So that will be everything for this tutorial. I hope it was useful. We have reviewed how to calculate the different options of distribution coefficients. So thank you for watching and have a great day.